Hi everyone and welcome to our discussion for Book 1, Proposition 15 of Euclid's Elements. Proposition 15. If two straight lines cut one another, then they make the vertical angles equal to one another. In this Proposition 15, we have an introduction of the term vertical angles and of its parameters being equal to each other. And we produce vertical angles when we have two lines, for example, CD and AB. These two lines cut one another, intersects, and passes through each other. Proposition 15 is being cited when we are identifying or using an unknown angle, which is vertical to a known or leading angle. And in discussing the figure and the proof, here are our components. The first one will be guided by the parameter of angles in the same line. It states that the sum are equal to two right angles, and that is at proposition 13. And we also have right angles being equal each other at postulate 4. And we also have a common notion for adding and subtracting angles. And for the proof, using the parameter of angles in the same line, it states the sum are equal to the two right angles and also the parameter of right angles being equal each other. We can establish equalities or equations. And upon comparing equations, we can have the subtraction of common terms. And then we would be able to derive the equality of the vertical angles. Corollary. When we say corollary, it means a claim or statement which is a result of a certain proposition. So, corollary to proposition 15, we have this statement. From proposition 15, it follows that if two straight lines cut one another, then they make the angles at the point of section equal to four right angles. So what do you mean by the corollary? Okay, so for example, we have line CD and line AB. So they intersect and passes through each other, right? So here, if we would take a look at line CD and with line AB intersecting it, we have the northern hemisphere and the southern hemisphere. And here at the northern hemisphere, with line AB intersecting line CD, we have two adjacent angles here. And the sum of two adjacent angles, because they stand on the same line, will be equal to two right angles. So you have two right angles at the northern hemisphere. And at the southern hemisphere, again, with line AB intersecting line CD, then we have two adjacent angles here standing at the same line CD. Then we have another two right angles here. So the total, okay, for this figure for the northern hemisphere and the southern hemisphere would be four right angles. And the same goes when we have line AB as a common line or the starting line and CD intersecting. Okay, so we have the eastern hemisphere and the western hemisphere. So here at this side, again, you have two adjacent angles, so that would be two right angles. And here at the western hemisphere, then another two adjacent angles, so two right angles again. So we're gonna sum up the eastern part and the western part, then you have four right angles. So that's the corollary of proposition 15. So let's discuss the detailed steps of the proof. So first of all, we have to define all of the angles. So let's replicate the figure. So we have AB and we have CD. Okay, all right. So let's identify the angles. So we have C, and then we have the common point, E. Okay, all right. So CEA here, and then we have AED. Okay, and we have GEB here and BEC at this side. Okay. Second, we will identify the equation, okay, within line CD and lines AB. So we'll consider the northern hemisphere of line CD, this part. Let's draw an equation based from the proposition 13, sum of the adjacent angles equal to two right angles. So we have then CEA plus AED. Okay, sum of angles. And then we also have within the line AB, this one. The same mindset, the same procedure will consider proposition 13. And we'll consider the western part, the western hemisphere of AB, the west part of AB. This one, these two angles here. So these are the two adjacent angles, and they're standing at the same line. So the sum of these two angles is equal to two right angles. So we're adding BEC and CEA. All right. And since both hemisphere, this part, the northern part of CD, and the western part of AB, since they have a common denominator, a common ground of having its adjacent angles equal to, or the sum of the adjacent angles equal to two right angles, then we can have this statement. CEA plus AED is equal to BEC plus CA. So this is the first statement that we have derived based from the parameter of proposition 13. Again, proposition 13 states that the sum of the adjacent angles will be equal to two right angles. Okay. And by elimination, we have a common term here, CEA, as you can see. Then we can eliminate CEA here and CEA here. Then we have AED equal to BEC. Now we have to show that AEC is equal to DB. So we have to show which hemisphere has the DB, and then identify and derive another equation. So we'll consider AB at the west part and AB again at the eastern part. Because at the eastern part, we have the DEB. So again, two adjacent angles at the same line will be the sum of those two adjacent angles at the same line will be equal to two right angles. So we have AEC plus BEC, AEC plus BEC equal to DEB plus AED. Again, the sum of the adjacent angles standing at the same line will be equal to two right angles. So we have this equation. And then by substitution, so we have here AED equal to BEC. Okay, so in this equation here, we have BEC. So we will substitute it with AED. That's why we have here AEC plus AED. And we will just bring this down here, GEB plus AEB. And by elimination, we have a common term AED here. So we will eliminate AED here at this side and AED at this side. Now we have AEC equal to DEB. So again, the focus of the proof is the usage of the proposition 13, that the sum of the two adjacent angles lying in the same line would be equal to two right angles. So thank you so much for listening and watching, and stay safe, everyone. Take care.